In this video, we're going to take a look at the semantics of our fragment of English. We're going to take a look at the meanings of the terminal nodes, so our words and our connectives, take a look at the meaning of our nouns and VPs, and the meaning of S. And then in the next video, we're going to learn how to draw an entire syntactic tree. So as a reminder, if alpha is a well-formed expression of F1, this just basically means that it is grammatical and drawn according to our syntactic rules in F1. Then we put the double brackets around alpha with a V above it, and that's its semantic value in that circumstance V. So if we have Jack in these semantic value brackets, then that is the semantic value of Jack in circumstance V. So these go for words, connectives, and phrases. Now, at the sentence level, if S is a well-formed sentence of F1, then S denotes the truth value of S in some circumstance V. So sentences have truth values. This is 1 or 0, while words and phrases have elements or set meanings. So if we write that SV is equal to 1, that just means S is true, and SV is equal to 0, that means S is false. This is very similar to propositional logic. Okay. Now, to interpret a syntactic structure and to do semantics on it, there's two things. We need every single terminal node to be assigned with a lexical value. So a terminal node is something that ends the sentence. So if we have, I don't say Jack, and then lies would be our intransitive verb, the terminal node is the thing at the bottom. So Jack and lies would be terminal nodes. So those need meanings. What we also need is we need every syntactic rule to have meanings. So for instance, we need to get the meaning of a noun. But the requirement is that the meaning of that node or that phrase is only determined by the meanings of everything below it. So the noun has to be determined by the meaning of Jack. The intransitive verb has to be determined by the meaning of lies. The verb phrase has to be determined by the meaning of the intransitive verb. And then the sentence, well, this can be determined by the meaning of the noun and the verb phrase. So it's a node gets its meaning from its daughters in some form. So there's three different ways that we can represent a syntactic tree. We have different situations where we use each of these. Typically A arrow BC. This is what we use for syntactic rules. So like we had before, we had S to say the negation of S. That is a syntactic rule. Typically, we use the brackets. So little a in the inside of the brackets, then BC. We use this for semantic rules. These both mean the same thing. So these both represent the same thing, but we just use them in different circumstances. And finally, this is the one you're more familiar with, probably A branching into B and C, and this is what we just use for syntactic trees and semantic trees. So we'll see all three of these different notations, and we'll use them all in their respective domain. Okay, so let's start by talking about the meanings of the terminal nodes and the connectives. Whenever we have a proper name, like say Jack or Sophia, its meaning is just an object, it's an element. And typically what we do is we specify that with either the name or a single letter, and we put a little prime symbol next to it. So the meaning of Jack in some situation V could be Jack prime, or we could just call this J prime for shorthand. So when we do say Sophia 2, the meaning or the value of Sophia in some situation would be Sophia prime or S prime. If we have an intransitive verb or a transitive verb, we just write them as relations. So is boring would be the set of X such that X is boring in V. We have to specify this. We have to say in that situation. Sleeps, this is an intransitive verb. It's the set of X such that X sleeps in V, in our situation. Likes, this is a transitive verb, so we need pairs here. There's a subject, there's an object. We don't know what they are yet. So these are pairs XY, where X likes Y and V. Once again, we specify in V to know we're talking about in our situation. So those are what our words will look like. We have a couple more words to define. a couple more types of words, and these are our negation and our conjunction. And what we do here is we basically write our truth tables out in matrix form. So what this means, it is not the case that. What is the meaning of that? Well, this says if you have a 1 in the sentence, it goes to 0. If you have a 0 for the sentence, it goes to 1. So this is like our truth table, of P and not P. If we have 1, 0 for P, we go 0, 1 to not P. And that's exactly what this represents. 1 becomes 0. 0 becomes 1. So our truth values are just put into function form. With a conjunction, remember this takes two things. So if you have P, Q, then you get P and Q. So if we draw the truth table out for this, I won't use different colors for ones and zeros because at this point we're very familiar with it. This matrix representation is just the truth values, truth table, written out in function form. So this says it takes the first sentence, it takes the second sentence, it looks at both of those values, and then it pumps out the value for the entire sentence. So if P and Q are both 1, then the conjunction of those is true. If sentence 1 is 1 but sentence 2 is 0, then the conjunction is 0 because only one of those are true. And that would then represent this second row in our truth table. I haven't defined or here, but I'm sure you could be figuring out or at this point, probably right off the top of your head. So if you had or here, then let's just scribble them out and put it out explicitly. This would be a 1110 truth table because in the second and third row, where just one of them is true, or would be true in those situations. So that's how we do our terminal nodes. We now have meanings for all of the words at the bottom of our trees. We now need to figure out what the other nodes are. So if we have S, N, VP, VT, N, well, at this point, Jack likes Mary. Okay, we're able to do these three. So this would be, say, J prime, Mary would be M prime, and likes would be pairs XY, such that X likes Y in V. Okay, so now we need to figure out what the meanings of the VT is. N, the VP, the N, and finally the sentence level. So we're going to go through each of these rules step by step. And for each of these rules, I have the formal rule listed, and I have an example. So the left side of these examples is just the words themselves. The right side is what the tree looks like. So the first rule says, if A is a category and little a is a lexical entry or a category, then the meaning of a little a, so the meaning of this structure is the same as just the meaning of little a itself. So what this says is that if a node only has one daughter, it just gets the same meaning as its daughter. So for example, if we have a proper name Jack, well, Jack is a word at the bottom. So it starts with Jack, and then this builds up into a noun. So what this Passup rule is saying is that whatever the meaning of Jack is, J prime, it's going to be the same meaning as the node above. And when we write out meanings, we make sure we do two things for non-terminal nodes. We write out the rule, and then we write out the value. So the meaning of the N node is the same as the meaning of Jack, and that would then be Jack prime. And this is determined by the meaning of Jack prime in the lower node. That's the terminal node. Let's say we have an intransitive verb is hungry, and this comes from the word itself is hungry. Well, we know what in hungry means. It means the set of X such that X is hungry in V. So the meaning of the VI is the same as the meaning of is hungry. It's the same as the meaning of the node below it. And that meaning is the set of X such that X is hungry in V. So what we have here is we have a rule and we have a value. It's important to write the rule down so that way we know where we get our meanings from. So this is called the Passup Rule. Well, I call this the Passup Rule because it's what it does, is it takes the meaning of the lower node, its only daughter, and it takes on that meaning. It's kind of a boring rule. Let's go with the more exciting ones. Okay, transitive verbs. If we have a verb phrase, so a VP, that consists of a transitive verb and an object, well, we have a specific rule for this. Remember, when you have a transitive verb, you're looking for pairs of things X and Y. Well, when you take an object like Sophia and you bring it into the verb phrase, you get likes Sophia. So at that point, we're no longer looking for our direct object, because we have it. We're only looking for a subject. So what the rule for the verb phrase says is that now we're looking for the set of x, such that x and our direct object, which we know what it is now, is just an element of the transitive verb. So I like to show an example because I think it makes this rule more clear, and then you come back to the definition and it kind of makes sense how things work. So the transitive verb, likes, is expressed as the set of xy such that x likes y and v. It's a transitive verb, so we're looking for pairs of things. We're looking for x and y, subject and direct object. In this example, we have a noun, which is Sophia. So the meaning of that is Sophia prime. So when we look at the verb phrase, now we're looking at the set of x such that x likes Sophia prime in V. This is essentially what we're looking for. Because this used to be a y. We used to be looking for pairs xy. But now we know what y is. So we substitute the meaning of that noun, which is Sophia prime, into that y, and then we get our resultant meaning. So basically what this says is that we're looking at the set of x such that x and the noun are in a pair. And because we know what the meaning of the noun is, which is Sophia prime, we're basically looking for all the x's such that x and Sophia prime, that pair, are in the transitive verb. And this is the same thing as paraphrasing it and saying that x likes Sophia prime in V. So basically, we have our direct object, we put it in the pair because we know what the direct object in the pair is, and now we're just looking for subjects. Here's another example, ghosted Dave. Well, here you have a verb phrase. Ghosted is a transitive verb. Dave is our direct object noun. So we know the meaning of our transitive verb. It's the set of xy such that x ghosted y in V, because we're looking for a subject and a direct object. The noun, our direct object, is Dave prime. That's who is being ghosted. So we're looking for xy, but now we know what y is. Y is Dave. So at this point, we're just looking for x. So we're looking for the set of x such that x ghosted Dave prime or D prime in V. So that's our set x. And the rule is here. So we're looking for pairs x, n, that is in VT. We know what that n is. We know the meaning of our direct object. It's Dave. So we're looking for the set of x such that the pair x and Dave is in our transitive verb set, which paraphrases to the set of x such that x goes to Dave prime in V. Yeah, I think that's one of our more complicated rules that we have so far. And if you didn't quite get that, and you have questions about how pairs work, please feel free to email me or talk to me in office hours or an appointment, and we can go through that. Okay. Finally, this is our last rule that does not use connectives. This is the meaning of a sentence. So Jack sleeps. This is a sentence that breaks from a noun and a verb phrase. How this works is, remember, our subject is just an object. It's an element, it's a thing. Our verb phrase is a set or a relation that's looking for a subject. So maybe using the word object here isn't the best thing to use because that's set theory words and we're talking about linguistics, so we can call this element. So the sentence Jack sleeps is true if Jack is a sleeper. So we can think of this as being that the meaning of our subject is an element in the semantic value of our verb phrase. So in other words, if our subject is Jack prime and our verb phrase is the set of x such that x sleeps in V, then the sentence will be true if Jack is in that set, which is exactly what our rule says above. It's true if the subject noun is in the verb phrase. So if Jack prime is in the set of x such that x sleeps in V. Now, whether we have an intransitive verb or a transitive verb or even a ditransitive verb, it doesn't change how the rule works. So here's the other example. Jack likes Emily. Jack is our subject noun, likes Emily is our verb phrase. So if we take a look at the meanings here, well, Jack is going to be Jack prime still. Our verb phrase, well, what is the meaning of likes Emily? We're looking for the set of x such that x likes Emily in V. So if our sentence is true, Jack likes Emily, then Jack is going to be a member of that verb phrase. Jack prime will be an element of the set of X such that X likes Emily prime in V. If that condition holds, the sentence is true. If Jack is not a member of the set of people, X, who like Emily, then the sentence is false. Okay. So we get a lot of practice with these when we start building trees, but for now we're just going to go through the rules one by one and show these quick examples. 14. When we negate a sentence, what we do is we take the meaning of the sentence and we apply the negation function to it. So basically, what this means is that if we negate something that is true, that's 1, we're going to get a 0 out of it. If we negate something that is false, well, it's going to become true. So let's take a look at this example here. It is not the case that Jack sleeps. This is a sentence. It breaks up into two components. It is not the case that, our negation, and Jack sleeps, another sentence. So our negation is this function that maps 1s to 0s and 0s to 1s. And the sentence Jack sleeps is going to be true if Jack is a sleeper. So if Jack prime is an element of the set of X such that X sleeps in V. So notice here, it's true if Jack sleeps, which means when we negate it, it's going to be false if Jack sleeps. This is another way of saying that it's true if Jack prime is not an element of sleepers. So I wrote out 3 lines here. I only really need 2. I need the rule, which is the first line, and I need the value, which is the third line. I wrote this intermediate step so you can see the truth value changing from 1 to 0. But that's an example of negation. So let's do another one here. Let's say we have an S. Here's our negation. Then the value of the negation will always be the same, so we have to make sure that we write out the matrix 1 to 0, 0 to 1. And let's have the sentence be, I don't know, Steve likes Mary. Okay, kind of a boring sentence, but unfortunately, we can't really get too many exciting sentences in this part of the course. So Steve likes Mary. This is going to be true if and only if S prime, so Steve, is in the set of X such that X likes M prime, which is Mary, in V. So I didn't write the rule here because I'm just being quick. I should write the rule out there, but we don't have anything below it in this example, so why not just put the value there? And that means that this meaning of the sentence up here, V, well, this is going to be the negation on S. So we're going to take S and we're going to negate it. So now instead of it being true, if S prime is an element of the set of X such that X likes M prime in V, it's going to be false if that happens. So false if S prime is in the set of X such that X likes M prime. And I'm not going to write in V just because I need to save space here, but I should. So if it's false if S prime is in the set, that means it's true if S prime is not in that set. Okay, so there's 2 examples there. That's how negation works. The last rule we have, which yes is the last rule and last slide of this video, is the conjunction rule. If we have 2 sentences S1 and S2 and they're joined by a conjunction, we take the conjunction function and we apply it to S1 and S2. So basically, you could take and, for instance, the meaning of and, you could apply it to S1 and S2. So we could say 1 and 0, and that would pop out a 0. So I have 2 examples here. One, I have Jack sleeps and Kate is hungry. So let's call Jack sleeps S1, and as a conjunction, Kate is hungry as an S2. So I don't have the meanings of these S1s and S2s written out here. But if we have Jack sleeps, this would mean that Jack is an element of the set of X such that X sleeps in V. Jack is a sleeper. And Kate is hungry. Well, if that's true, then Kate should be in the group of hungry people. So Kate is an element of the set of X such that X is hungry in V. The conjunction for and is the truth table that is 1, 0, 0, 0. It's only true when sentence 1 and sentence 2 are both true. So when we write out our rule for the conjunction, we take the conjunction, we apply it to S1 and S2. We paraphrase this, so this is true if S1 is true and S2 is true, and then we replace the values of S1 and S2 with the conditions. So Jack is an element of X such that X sleeps in V, and Kate is an element of the set of X such that X is hungry in V. It's going to be the same thing for OR. The difference is we're using OR instead of AND. So the only real difference in our truth tree for this example, or truth tree, our semantic tree in this case, is going to be the outputs on our matrix. So 1, 1, 1, 0 instead of 1, 0, 0, 0. So when we do our rule, instead of conj S1, S2, giving S1 is 1 and S2 is 1, we have an OR here. So that's the difference between and OR. So our final result is going to be that this sentence, Jack sleeps or Kate is hungry, is true if Jack prime is the set of X such that X sleeps in V, or Kate prime is in the set of X such that X is hungry in V. So this video was just an onslaught of rules. In the next video, we're going to go through one detailed example. We're going to take a look at how the tree is built with all these rules at once, and then we're going to do a couple of practice questions and learn how to evaluate it in a world. So if there's any questions, again, discussion board email, I'll get back to you when I can.